Welcome to the fascinating world of polymer chemistry. Break down free radical polymerization. It is a key process for making common plastics. Free radical polymerization is a type of chain growth polymerization which free radicals initiate the reaction. We will go through each summations and real examples. From the basic monomer structure applications. Here is the layout of our full course. Let us begin this journey into polymer science. In initiation, a free radical is formed. During propagation, the polymer chain grows rapidly. Finally, termination stops the reaction. A simple start, a fast growth, a stable finish.
Let us master free radical polymerization together. We will break down the entire mechanism, from initiation to chain growth. Let us get started.
Today in this explainer, we are putting the vinyl chloride monomer on a strict 60-second clock. It is quite literally a fundamental building block of modern materials, and we're going to break down its 6 core facets right here, right now. Ready? Let's go. First up, we've got to cover the basics. The molecular formula here is C2H3CL, clocking in with a molar mass of exactly 62.50 grams per mole. But honestly, the real star of the show, the engine that completely drives this molecule, is that highly reactive carbon-carbon double bond sitting right smack in the center. So zooming in on that double bond, you'll see this is the exact site of addition polymerization. And it basically relies on 2 distinct layers. You've got a really strong foundational sigma bond holding things together, and then that's paired with a super reactive, heavily electron-dense pi bond. Now, when you visualize the electron cloud, you can actually see that the density isn't uniform at all. It's not spread out evenly. Instead, those electrons are heavily concentrated directly around that central double bond, and they really pool around that big chlorine atom. Okay, let's dive down to the quantum level for a second. This molecular orbital view shows us exactly how that energetic pi bond actually forms. It happens through the side-by-side overlap of these p orbitals, which are functioning right alongside those sturdy CH and CCl sigma bonds. But here's the thing about how this works in 3-dimensional space. The molecule actually faces some pretty strict physical constraints. While the single bonds have total freedom to rotate around, movement is entirely restricted around that rigid central double bond. I mean, it is locked firmly into place. No twisting allowed. So, pulling this all together, here's what you really need to know. That massive chlorine atom completely dictates the molecule's overall polarity and reactivity. And that specific electrostatic setup is what drives this phenylic monomer to undergo addition polymerization. Basically, it snaps these individual chains together over and over again to form a polymer you definitely know, ubiquitous PVC.
An organic peroxide initiator is introduced. It features a notoriously weak oxygen-oxygen bond. This bond is easily broken by heat or light energy. In homolytic cleavage, a shared electron pair splits evenly, forming 2 highly reactive free radicals. Bond cleavage produces 2 alky free radicals. Each radical contains an unpaired electron, making it highly reactive. These species seek out other molecules to react with, propagating a chain reaction. The free radical approaches a monomer molecule. The carbon-carbon double bond contains a reactive pi bond. This region is rich in electron density. The radical is now positioned. It attacks the double bond. This initiates the chain reaction.
Welcome to the process of free radical polymerization. The initiator approaches the vinyl chloride monomer. The high-energy ball attacks the double bond.
Watch as this free radical attacks. It targets the electron-rich double bond.
Notice the curved arrow indicating the precise movement of the electron pair. This is how monomers polymerize. Notice how the free radical attacks the pi bond. One electron forms a new bond, while the other remains. This leaves a single unpaired electron on the carbon, and that is how the reaction begins. Behold the generated radical. This center is highly reactive. Notice the hyperconjugation. This is advanced chemistry. This is advanced chemistry.
Column B. It pertinenid sixtenid farsin prescendeds to a polymer chain. Is intrimaches minigical broad chain.
The initiation step is complete, leaving a highly reactive, unpaired electron. This active center pulses with energy, ready to attack, to the next unit. Now we will demonstrate radical approaches to create a new monomer. Watch closely as the growing polymer radical chain moves toward a nearby vinyl chloride monomer. In step 3, the radical attacks the double bond. The pi bond breaks as a new car-carbon bond forms. During chain extension, the polymer grows. A monomer inserts at the active center, relocating the radical to the new chain end. In the propagation cycle, another monomer approaches the radical. It inserts itself, and the active center shifts. This process repeats rapidly, continuously elongating the polymer chain. The active radical center, on the growing chain, attracts rapidly new monomers. In the propagation phase, the active radical center continuously attracts surrounding monomers, rapidly extending the polymer chain. This is an organic peroxide initiator. The weak oxygen-oxygen bond is the key feature. Because this bond is unstable, electrons shift. The bond is ready to break.
Organic peroxide molecules can be activated when they absorb energy from their surroundings. Heat or ultraviolet light can provide the energy needed to weaken the oxygen bond.
An organic peroxide contains a weak oxygen-oxygen bond that can break when energy is applied. During homolytic cleavage, the bonding electrons divide equally between the two oxygen. The oxygen-oxygen bond is weak. The bonding pair separates evenly. This creates two highly reactive radicals. They continue to drive reactions. A free radical contains an unpaired electron, making it highly reactive and ready to form new bonds. The radical moves toward a vinyl chloride monomer to begin the merization process.
In the termination step of free radical polymerization, growing polymer chains stop reacting when their radicals are removed. In combination termination, two polymer radicals join together by pairing their unpaired electrons and forming a new covalent bond. Once the radicals disappear, the polymer becomes stable, and chain growth completely stops. Check the next pathway! Another pathway is disproportionation termination, where one radical transfers a hydrogen atom, forming a double bond. Sheesh, that double bond is bussin'! After hydrogen transfer, both polymer chains lose their radical activity and become stable polymer products. Termination ends polymerization. It removes reactive radicals. Use combination or disproportionation. Stick, it's lodcax.
During free radical polymerization, chain growth continues as long as the active radical remains at the end of the polymer chain. The radical can transfer to another molecule. In chain transfer, the active radical does not disappear. Instead, it moves to another molecule. The original polymer stops growing, while a new radical site is created. Chain transfer can also happen when radicals react with solvents, oxygen, or impurities. These unwanted reactions reduce Sometimes chain transfer creates branching. Instead of forming a straight polymer chain, new growth starts from the side of an existing chain, producing a branched structure. Side reactions change the structure of polymers. They can create shorter chains, branching, and irregular arrangements, which influence strength, flexibility, and material performance. Chain transfer and side reactions interrupt normal polymer growth. Although radicals allow polymerization continue, unwanted transfers can control chain length, create branching, and change the properties of the final polymer.
PVC is created through free radical polymerization. Monomers link together, forming durable chains. This process builds the foundation of modern infrastructure.
Free radical polymerization transforms vinyl chloride monomers into durable PVC pipes for critical infrastructure. Inspector Tung Tung Sahur keeps watch.
Welcome to the world of food science. Free radical polymerization creates amazing food packaging. It produces strong, protective films, keeping our food fresh and safe.
Here, we use free radical polymerization. Monomers quickly link into long polymer chains. They are extruded into durable cables and high-performance rubber for running shoes. Here, we apply free radical polymerization to create advanced, bio-inspired elastomers, synthesizing next-generation synthetic rubber. The polymer chain is perfectly stable. Inside this sterile facility, a precise process begins. Free radical polymerization links monomers together, transforming these chains into high-quality medical tubing. The process begins with the vinyl chloride monomer. Through chain elongation, it transforms into versatile PVC products.